Hello, dear viewer. Today I'll attempt to relay the intuition and maths behind how ZK-SNARKs are possible. In case you haven't heard of them before, ZK-SNARKs are a cryptographic protocol that lets you prove that you've done a certain computation to someone else while, 1, hiding some of the inputs to that computation, and 2, requiring the verifier to process a proof that's much smaller than the original computation. Specifically, what this means is that you can make a large computation on private data and make certain assertions to it to somebody else. For instance, let's say you're checking the age on an ID and you want to verify that the ID not only is real, but also that the person in front of you matches certain aspects about the ID without showing it in its entirety. You can do that. Or for example, if you want to play a video game and then make a proof that you have in fact achieved a certain time for a speedrun without showing exactly what you did, or without revealing maybe your secret strategy, you can use a SNARK for that. So in this video, I'll dive into the maths that make it possible, because at first it seems kind of impossible, right? How can you take a big computation that's maybe, like for example, a game can run over kilobytes or megabytes of memory for, multiple minutes, and then give you like a tiny, proof that's like not bigger than a text message, and you can verify it in less than 10 milliseconds, right? How is that even conceptually possible? It seems kind of impossible. So I'll go into the different pieces of math and slowly wind them together to try and give you an understanding of how this is possible. To start to explain how this is even remotely possible, I'll bring you back to some early high school math, polynomials. For those who don't remember, polynomials are simple functions that take in inputs and map it to some output. But these are specific kinds of functions. These are functions that are specifically simple to write. They have the form of like x to the n times some factor plus x to the n minus 1 times some factor put together. In this diagram, we have two very simple polynomials. We have a parabola, which is x to the 2 plus x plus some constant and some factors, and a line, which is also polynomial, but it's just a very small one, right? A degree 2 polynomial because the one has a power of 2, and a degree 1 polynomial because it's a power of 1. And we want to talk about where they intersect and how they are the same, because these two lines that represent polynomials are obviously not the same, but they're the same at certain points, right? So now if we want to see where they're the same and actually like basically solve the equation and find these points in a general manner, you'd want to check where they intersect. So to do that, let's set up the equation and let's call the parabola f of x and the line g of x. And mathematically, if we want to see where they cross, this is just saying, okay, when is the left side equal to the right side? And then here are the polynomials. So this will actually give you a view of what they look like. And solving this just amounts to bringing it all to one side so we can equal to 0. And now we have this new polynomial, x squared minus 4x plus 3, that when it's 0, it tells us where the two polynomials intersected, right? And in this case, we already know the answer, so it's 1 and 3, right? And if you go back to the graph, you'll see it's 1 and 3. The thing you'll notice here is that the maximum amount of points where two of these polynomials can intersect is based on their so-called degree, right? On the highest power. So if it's a power of 2, then in theory, like at most, they'll intersect at 2 points, but they may intersect at fewer points, right? So we can generalize to say that if you have a polynomial of some degree d, they'll have at most d intersections, right? Because when you subtract them to bring them over to one side and do this equation, it'll result in a polynomial of that degree. And that degree has at most that many zeros, which means those polynomials could have had as most that many intersections. So now if we want to, now we can use this fact to easily check where the two polynomials are the same. So let's imagine like some really huge polynomial. Right there we just had small polynomials. So we had a polynomial of degree 2. But let's imagine a polynomial of degree 1,000,000, right? Where you have 1,000,000 coefficients, and this input can have a bunch of different values, but specifically it means that at most one of those polynomials can have 1,000,000 zeros. And that means if you have two of these polynomials of degree 1,000,000, they can intersect at most at 1,000,000 points. So what if we wanted to easily check whether two polynomials were the same. Well, what if we took a number that's much larger than that? Or randomly took a number that's in a range much larger than that. For example, a 256-bit number. So a number in your computer that consists of 256 zeros, right? So very feasible to actually like pick, but much, much larger than 10 million, right? And then we compared these two polynomials at that point. Well, if the polynomials are not equal, so meaning they have different coefficients, they can still intersect, right? They can still be equal at certain points. So what's the probability that they'll be equal at the random point we picked? Well, they only have 10 to the 6 or 1 million degree, right? So they can only intersect at 1 million points. But we picked a number from a range that's so much larger than that. So the probability that we accidentally picked one of those points where they happen to cross is extremely small. So we can say that if they happen to be the same at this point, right? If we put our value into the first function, we get out a value, and we put in the second function, we get out a value, and we compare those, we see that, oh, hey, these are almost definitely not the same. Now, if you go back, you'll see that, hey, like they can be the same, but the probability is so small that we can almost for certain say that if they're the same at some random value picked from a large range, they're almost definitely the same. And mathematicians refer to this as the Schwarz-Zippel lemma. Now let's go back to the actual cryptography and think about what our goal is, right? We want to take something we care about, some statement, some computation, some calculation, and we want to express it in such a way such that we can convince somebody that we ran it correctly and got a certain output, and maybe even hiding some of the inputs, but in a very, very concise way. So to make this simple for us, instead of thinking about all possible computations and how they look like, we want some basic component that stacked together sufficient times can express any component. Like for example, in math, you have addition, multiplication, and if you think about it, most math is just a stacking of that on top of one another, like even derivatives, even fancy calculus things, they're all just addition and multiplication in very fancy ways. Even exponents, they're just repeated multiplication, or even division is just multiplication reversed, right? So if you think about it like that, similar to that in computers, you can take a component and electronics and you can stack them on top of each other, like transistors, to create a very complex thing from very simple pieces. So we'll start with that here as well. We'll go a bit more complex than transistor, and we'll take a so-called logic gate, a NAND gate. The reason we're taking this gate is because it's very general. If you look for information about it online, you'll see that in general it's possible to construct any other logic gate from a NAND gate, and from that you can construct any kind of computer circuitry, any kind of CPU theory, and really build up a full computer. So a NAND gate, a logic gate, is just a fancy way of saying it's like a little component that takes in some inputs and gives you an output. It's almost like the functions we talked about before, but kind of different. So they take in some inputs, give some outputs, and in this case, the inputs and outputs it gives us is very simple, right? It's binary, so it's literally only two possibilities for each input and two possibilities for the output. And then this table tells you basically what you get out when, right? So if you have two zeros, you get out a 1. If you have 1 0, you get out a 1. If you get 0 1, you get a 1. And 1 1 is the only set of inputs that gives you a 0. All right, so basically this gate is checking that at least one of the inputs is a 0. So let's express this mathematically so we can start doing some trickery on it to cheaply check it, right? Because in this case, if our goal is to convince somebody that we ran the NAND gate on a set of inputs, it's quite simple, right? You send them over literally just two numbers, and they just check the output themselves. But what if we wanted one of our inputs to be secret? Or what if we wanted 100,000 NAND gates and to prove to the person that 3 inputs were this and the rest is all hidden, right? Then sending over all the values will be quite expensive and quite slow. So what we do is let's start with one NAND gate, and then at the end you'll be able to imagine what it looks like with more NAND gates. Right, so expressed mathematically, let's say that our inputs, we call them A0, A1, and we have our output. And now we want to express this as an equation, right? So if this equation is true, the NAND gate gave us 1. And if the equation is not true, it equals 0. So this is slightly confusing, but we can express this as a0 times a1 is equal to 0. So remember, we're checking whether the NAND gate gave us 1, but the reason we're checking if a0 times a1 is equal to 0 is because if you think about it, when this equation is true, i.e. when the result of a0 times a1 is actually 0, the NAND gate gave us 1, right? Because any of the two inputs has to be 0 for it to be successful. Versus if a0 and a1 are both 1, then this equation is not true, right? Because 1 is not equal to 0. So this sets up, as people in ZK or cryptography like to call it, a constraint. We constrain our inputs, and we're creating an arithmetic circuit. So this is a fancy way of saying we're taking this electronic circuit and we're turning it into math, into arithmetic. But if you run it through some examples, we're dealing with math here now, no longer electronics, right? So our numbers, they're numbers, right? What if it's not 0 or 1? What if it's 3? It will still be valid, right? 0 times 3 is still 0, so it'll still pass, but that's incorrect, right? That's it's just nonsensical, right? You don't have a binary value that is 3. So to further check that these values are 0 or 1, we add further constraints. That's check whether a0 or a1 are both only binary in a similar format. And this is generally what you do if you want to turn your computation into a SNARK. You just set up all these constraints that are math versions of saying what your computer would say, right? And if you'll notice, these constraints are in special form. They're multiplication equaling 0. Now, the actual Groth16 scheme, which is kind of what we're explaining here, you can actually put variables on the right side too. But for simplification's sake, we'll say we're only allowed to do equals zeros here, because this is enough for our example, and extending it to do that is quite simple, but it adds a lot of symbols. So let's look at these three constraints more closely, and let's further process these into math. Well, they each have a left and right side that are multiplied together, right? So if we want to kind of express this in some standard form, we can say that on every row on the left, we can have all three of our variables, right? We can have the a0, a1, and 1, just that in the first row on the left, they're not used, right? So if we just add a factor here to kind of like select them, we can imagine these are like selectors that go in and choose like which variable we're using in every row. We can express these like just like 1 if we're using a0, or 0 if you're using the others. In this case, you could also set it 2 or 3 or some other factor, but in this case, we don't need that, so 1 and 0 will be enough, but this could be any kind of number. So if we think about it, this can just be a matrix, right? If we take out the values, we can represent this as a matrix where the columns are what variables are being used, and the rows are the rows or like our constraints, right? Numbered 1, 2, 3. And we can do the same thing for the right side, except, for example, on row 2 to the right, we not only have a0, but we also have a 1, right? So we're putting 1 times a0 plus minus 1 times 1, right? And we have a 0 for the a1. So let's look more closely at the right side, specifically the middle column. There's no reason we're picking the middle column. It's just a more interesting example, and we'll put an example equation here. So I'm going to give you this equation out of thin air, but there's an algorithm to create it. It's called polynomial interpolation. There's different ways to do it, like Lagrange interpolation, Fourier transforms, different ways you can do it, or just like manually solving an equation. But I'll just give the result to you here, which is V2. So if you think about V2, what it does is that if you give it the number of a row, 1, 2, 3, it'll give you the selector for that cell. So for example, in this case, it'll give us a selector for A1, right? So if we plug in the values 1, 2, 3, and we run through the calculation here, you'll see it gives 1, 0, and 1. Exactly what we want, right? So it's a polynomial, it's an equation that represents the middle column. And then representing it that way, we can just replace that. And the same goes for left and right. We can create equations that represent the entire column with one equation. So it's still 3 values, right? We still have 3 coefficients, but they're no longer the actual values that we had before, right? It's no longer 0, 1, 0. It's V1 of 1, V1 of 2, V1 of 3. And same thing for the right column, right? It's no longer 0, minus 1, minus 1. It's V3 of 1, V3 of 2, V3 of 3. And why we're doing it this way, this seems like a very complicated way of doing things. The reason we're doing it this way is we can start to move things towards being one big polynomial, and if you remember a trick from the beginning, we'll be able to easily check that a certain thing is the same, and that'll tell us something about the computation. But let's not get too ahead of ourselves. So take these three equations, and if you don't believe me, just take them to your calculator, plug in the values 1, 2, and 3, and see what their outputs are. And you'll see that it's the same as the matrix we had before. So pause here a second if you think it's a bit strange. Take a calculator or a piece of paper, plug in the values 1, 2, 3 for x in these three equations, and see what their outputs are. And you'll see that it's the same as the equation before. And if you're interested in how these are created, again, look up polynomial interpolation. There's different techniques based on your situation. So if we think about it, putting these things together, you'll see that each of these selectors are selecting one of our variables, right? One of our inputs, or in cryptography, these are called witnesses. So A0, A1, and a constant. So if we multiply and add these together using the polynomials we have, we get one big polynomial, VA of x, that now represents our entire right side, right? Because again, V1, V2, V3 for the row numbers gives us the selectors. And remember at the very beginning, the way we got this table in the first place is we just thought about what needs to get multiplied by our variables to get the given cell on the right side, all right? So just to really illustrate that this is in fact just what we had at the beginning, that this actually represents the right side, I'm going to go through and I'm going to plug in all these equations and plug in a value and show you that the result is actually the same as we had before. All right, so specifically we're going to do the second row, second constraint on the right, right? So we're going to plug in 2 into VA, and we're going to get out A0 minus 1. So let's do this. And before we do that, remember that we can actually do the same for the left side, right? So we can create a equation, we'll call it UA of x for this whole thing. So the reason we call it UA and VA is because we have V, which is just like the actual polynomials, now multiplied by A, right? And A is, you can imagine, as a vector containing all our witnesses. But let's give you one example to see what this monstrosity of an equation is actually doing. So we have this equation, and let's actually put in 2, right? To see that on the right side, row 2, we get our A0 minus 1. So we put in the x, which is 2, and we exponentiate it. Then we multiply all the brackets and put it everywhere, right? Then we remove the fractions where possible, and then we only have simple values left. We rearrange the values so that the A0s are next to each other, the A1s are next to each other, and the constants are next to each other. And you see that it'll all cancel out into what is at the end, A0 minus 1. So if you think about it, if you give 1, 2, 3 into this huge equation, it'll give you the values for our rows on the right. And UA will do the same for the left. Now this equation looks super complicated at the start, and it kind of is, but it becomes much simpler once you start plugging in concrete values for A0, A1. So if we actually ran our circuit on, let's say, the inputs 0, 1, and you plug them in, then they'll all squish down and it would be much simpler calculation. All right, so now let's actually move to imagining we want to prove a certain input, right? So we're going to prove that for an AND gate, if you give the inputs 0 and 1, it's going to give you 1 from the NAND gate, which means our equations will be satisfied, right? That means that all 3 rows will equal 0. And we're going to put these inputs together into a vector called A, which is a witness vector. And don't forget, we have this one constant that lets us do like the minus 1 stuff. So let's put it in. And let's take our equations. And you see the equation from before VA simplifies down a lot, right? It becomes this little fraction now that we've actually put in concrete values. And we can multiply these polynomials together, right? To get one big polynomial. And now what this means, what does this equation even mean, right? It looks very complicated. But it just means it represents our entire circuit as one big function, right? If you plug in 1, 2, or 3, because our inputs are valid, they would equal 0. right? Because we're multiplying something times something in every row that'll equal 0. And if these functions represent every single row, then inputting 1, 2, 3 will equal 0. Now, try and do the same for inputs that are invalid. So like maybe put in a 2 instead of a 0, a 1. Or maybe put in 1, 1. And see what the result is. And you'll see that it won't equal 0. So this equation only will equal 0 and 1, 2, 3 if the inputs are valid, right? And now we want to actually prove to the person. That's how we're going to show that we ran the circuit correctly. We're going to prove to the person that we have a polynomial, right? This ua of x times v of x that actually equals 0 at the first 3 points. And if we do that, that should convince them that it's actually correct. So the way we do that is first, let's imagine a much simpler function, much simpler polynomial that's 0 at 1, 2, 3. And we'll call this t of x. This is the vanishing polynomial, as cryptographers would call it. And we make it 0 at any points 1, 2, 3 by just saying x minus 1 times x minus 2 times x minus 3, right? Because if any of these brackets are 0, it will multiply out to 0. And notice that now it has the same 0 spots as UAVA. So because it has the same zeros, we can actually divide them. So you may not remember this, but you can actually divide polynomials, right? If they have the same factors. Similar to how you can divide 24 by 6 because it shares the same factors, you can divide two polynomials if they share the same factors. And it's just like, instead of dividing numbers, you're just dividing symbols. So if we go through this quickly and see, okay, what are these two polynomials, and reduce it down, we get this result. And note that this result only exists if your solution is correct, right? If you put in a 3 at the beginning, if you put in 1, 1, your resulting polynomial will not have zeros at 1, 2, 3. And this division will then have a remainder, because t of x by definition has zeros at 1, 2, 3, right? So if you try and do this division, you will have a remainder. It will not work. And now we just need to prove to some verifier that we have an h of x, that this h of x exists, and that we have an a and b. So instead of sending them over the whole polynomials, because then the larger your thing gets, the bigger the polynomial, the more calculations they have to do, we just evaluate it at a random point. So let's take a random point, let's call it tau, and then let's run it through our equations, and then we can send them over a, b, and h. And then all the verifier has to do, right, the person checking our calculation and making sure our NAND gate is correct, all they have to do is they multiply a times b, they compute t of tau, and then times h, and they compare the two, right? And the only way you would have actually created a valid version of this is if the functions behind a and b at the beginning, if they had zeros at 1, 2, 3, right? So it seems kind of magical, but remember, at the very beginning, we said that if we pick a random value from a large range and we plug it into a polynomial, we compare it to another polynomial, we know they're the same everywhere if they're the same at one spot. So although we're evaluating a tau, so tau could be some random value like 10,023 or 1,300,321, and our polynomial was only made really for the values 1, 2, 3, it can still give you outputs at other values, right? So if we input tau and check the values, this totally works. This is totally valid, and this is a way for us to check. So to make the calculation even simpler for the verifier, we will pre-compute t of tau, right? So when we create the circuit the first time, we will actually calculate t of tau once, we will fix tau, and then we'll always use tau for all our proofs. So no matter what input, you will take tau, you'll put it in your functions, and you'll get it out. And that's how you get the result. And then this process is called the trusted setup, right? So in practice, it's a bit more complicated than this, right? Because if you see tau, you can actually fake the proof. But on a high level, this is how it works. So now we have a full scheme that lets us easily prove that we had some polynomial that had zeros of 1, 2, 3. And this effectively proves that we solved our equation correctly. Now, if you're thinking a bit ahead, you may have a ton of questions related to the scheme, right? One, how can we not fake the proof if tau is fixed? How do we actually prove that we used our equation, right? Because this is only proving that you had some equation that is 0, 1, 2, 3, all of these things. So extending this to make it fully work is actually not that complicated. It just requires a bit more math, a few more variables. And if you're really interested, I highly recommend checking out the link in the description, which is a link to Rare Skill's ZK book, which goes through detail through each step of Graph 16, which is the ZK-SNARKs scheme we kind of attempted to explain here in a simplified manner. And that'll explain a lot of the details, and especially the last post in chapter 16 explains a lot of the extra details. But basically, if you want a high-level overview over how this works in reality, is that you're not actually computing on tau. First, tau is encrypted, right? So this prevents you from actually learning tau and faking a proof. But tau is encrypted in such a way where you can still compute your polynomial over it. You just can't see what tau actually is to try and fake the proof. Then there's some extra offsets to ensure that the trusted setup and the values there are tied to the actual circuit, the actual equation. And then put it all together, this makes a scheme that is actually private and secure. Additionally, there's the part I mentioned at the beginning where the actual shape of the equation in the actual ZK-SNARK scheme is not left times right is equal to 0, it's left times right is equal to output, right? Because otherwise there's certain kind of operations that you can't really do if it's like that. So yeah, if you're interested, look up Graph 16. If you look up the ZK book, you'll find the links in the description and they'll let you know more details. But I hope this was still a helpful overview to understand how basically cryptographers think of computation and how you can use math to slowly turn something basic into a bunch of complicated equations that then compress down into a single value that can be checked while still retaining indirectly the information about the beginning such that it actually validly checks. I hope this was useful to some extent. Please feel free to add comments to what you thought was helpful, what you thought was unhelpful, and maybe we'll make such a video in the future. Thank you for listening and have an amazing